Hello, everyone. I hope you had a great lunch and you're ready to hear a bit about Bayesian approach to robust reinforcement learning. This is a joint work with Daniel Mankowitz and Timothy Mann from DeepMind and my supervisor, Professor Shai Manor at the Technion. So there are several reasons why we need to introduce robustness into reinforcement learning. In general, we don't know the parameters of an MDP or the dynamics. We rather estimate them from historical data, and this can result in errors. So when we optimize the policy with respect to this estimate, the performance can significantly degrade if the dynamics are slightly different. And also, when doing regular reinforcement learning, a regular policy can be highly sensitive to changing or adversarial system behavior. And this sensitivity is highly unacceptable in certain domain applications such as autonomous driving or medicine or manufacturing. So for example, you don't want your policy to be sensitive to slightly different weather or traffic conditions. So this is why we introduce robustness. And the framework is that of robust MDPs. We have SNA, finite state and action spaces. R is the deterministic and bounding reward function. And instead of having only one transition matrix, we have a curly P, which is a set of transitions, such that P is structured as independent sets for each state and action. And I would call this structure as the rectangularity assumption. This is how it's called in the literature. And for each state and action, PSA can be a confidence interval for our estimate. And a robust optimal policy will be the one that maximizes the value function, but the worst one with respect to the uncertainty set. So instead of having the maximum of the expected reward, we have the maximum of the infimum over the uncertainty set of the cumulative reward. And so this rectangularity assumption, as I mentioned, can lead to overly conservative behavior. Because, for example, instead of taking the worst trajectory, you will take the worst next state transition for each state and action separately. And there have been several works that try to relax this assumption without altering tractability. Another reason why this robust framework can be overly conservative is that this set is initially fixed. So the robust policy cannot adapt itself to more advantageous scenarios. And in our work, we focus on this second problem of a fixed uncertainty set. And we place ourselves in a Bayesian framework. We have a prior over the next state transition. We have an observation history. And we construct a confidence interval around a nominal transition. And by construction, this uncertainty set is rectangular, so the problem is still tractable. We can compute the robust value function. But oppositely to regular approaches, this set is updated according to new observations. So we can apply the regular robust reinforcement learning method and compute the robust Q values with respect to the posterior. And the posterior worst case transition is the worst one with respect to the posterior uncertainty set we defined previously. So as I told you, the uncertainty set varies across different observations. So we can define the posterior variance of the robust Q values. And this will account to changes in the uncertainty set. And the nice thing about this variance is that it satisfies a Bellman recursion. So more precisely, this posterior variance is bounded by a quantity that satisfies what we call URBE, uncertainty robust Bellman equation. So here, instead of having the regular reward, we have a quantity that we call the robust local uncertainty in USA. And if the prior is Dirichlet, we can show that it is bounded by a positive constant divided by the visit counts. So this Bellman regression and this bound enable us to estimate the variance, and we will use this as an exploration bonus when doing robust reinforcement learning. So to start with a simple MDP, we have an agent that starts at S0, and it could choose one of 4 actions. If it chooses action A1, it gets a deterministic reward of 0.14. And if it chooses one of the other's action, it can get a high reward, but it is also subject to adversarial transitions. And in that case, it gets a bad reward. And these adversarial transitions occur with a certain probability. And in the robust policy here will consist in always taking the first action and securing a reward of 0.14. And you can see in the right-hand side that the robust policy is overly conservative. The green plot corresponds to posterior sampling when adding a variance bonus that corresponds to the variance of the posterior variance of the regular Q value. So you have an uncertainty set, and we see that it underperforms our approach of URB. So the problem here is that for each step we need to solve a robust optimization problem, which is highly costly, and this is not applicable to deep reinforcement learning. So we adapted what we call our DQNURB network, which is described as follows. So it's basically a neural network that has 2 outputs. The first output will compute the robust Q value based on the robust TD error, which is basically the current value plus the worst next state value. This is for a fixed uncertainty set, and the second output will compute the variance of this, and we call this the URB layer. And what the agent will act according to is a sample from a normal distribution centered at the current robust Q value, and which has variance, the second output of our network. We tested this on a grid wall domain where the agent starts in a random state from the red zone of the grid, and at each time it tries to direct itself to the goal state, which is in yellow in the bottom right. There's a certain probability that a bomb will explode, let's say, and in that case the reward will be very negative. So a robust policy will consist in staying safe and not getting toward the goal, and this is shown in the right-hand side of the slide in blue. So you see that even when the probability is low, the robust DQN doesn't try to get to the goal state. And the green plot and the black plot show DQN or DQNURB, which are overly sensitive to changes of this probability of failure. So when the probability is low, they do perform well, but as we increase it, the performance drops dramatically. And our UB approach is the one that does perform well on the nominal probability, meaning a low probability of failure, but is also robust to increasing probabilities. And to better visualize this, we plotted heat maps of the states visited by each agent when the probability of failure is 0.005, which is quite low. And on the left-hand side, we see that the robust DQN doesn't get to the goal state, whereas our URB approach does visit the goal state quite often. And when we increased this probability of failure, we compared our URB approach to the regular DQN. And we can see that in such a case, on the left-hand side, the regular DQN doesn't, or DQNURB, these have basically the same behavior. And these are overly sensitive to changes of dynamics, whereas URB does visit the goal state. And we tested also our approach to a carpal domain, and we can see similar behavior. So we trained our agent on a given pole length, and we changed it during evaluation. So as you can see, the DQN and GQNURB are overly sensitive to changes in the pole length, whereas the robust DQN doesn't perform the task at all, even on the nominal model. And our approach is the one that does perform well on the nominal and is robust to changes in the pole length. And during training, we also played with the length. So we basically waited for robust DQN and URB to converge. And once both have converged, we changed the dynamics of the model by changing the length. And as we can see in blue, the robust DQN is the most sensitive to changes of dynamics, and it doesn't recover to this change. Whereas our URB does perform the task and also recovers really fast to this change. So to conclude, we added URB as a variance bonus, and we showed that this leads to less conservative solutions. And we showed that DQNURB encourages self-exploration by implicitly updating the uncertainty set. And also we showed that it is able to adapt to changing dynamics online. What we didn't show is the asymptotic behavior of URB, because in the paper we only considered a finite horizon setting. And we also what would be interesting to show theoretically is to study the impact of the size of the posterior uncertainty set on the posterior variance of the robust Q values. So I'd be happy to hear your remarks and answer to your questions.